So far we've been talking about how to make inferences about a probability of success in one of two different scenarios. One scenario was that we had a population of homogeneous items where we couldn't necessarily differentiate one item from the next. Then we also looked at a situation where we had these items appearing in two different groups, so we could estimate the probability of success and make inferences about it for group 1 and group 2. Now we're going to talk about a situation where we have items that potentially appear in many different groups, and we would still like to make judgments, inferences about the probability of success for each particular group. These groups are going to be measurable in some way. We will refer to them as variables. And so to make this further extension of making inferences about probability of success, we need to now use regression models. And we're going to use what are referred to as binary regression models, because our response variable, still going to be called our y, has one of two different categories associated with it. These categories, just like what we've done previously, we're going to generically refer to them as a success category and a failure category. Now, first, before we get into these binary regression models and then also motivate their need, we're going to do a short review of normal linear regression models, which all of you should have seen at least a little bit in the past before coming into this course and before coming into my book. And so just to review, suppose again our response variable is y. Y can be a continuous random variable, maybe for example denoting, let's say, GPA level for a particular student, anywhere on a 0 to 4.0 scale. This response variable sometimes is also referred to as a dependent variable. And the reason why it's called sometimes a dependent variable is because it depends on some independent variables. Let's say that they're x1 through xp. So we have p different independent variables. Rather than me calling them independent variables, I like to call them explanatory variables because they are meant to help explain information about my response variable y. Some people will also refer to these explanatory variables as covariates as well. And so from a previous class, I don't know how that got changed there, you've seen a normal linear regression model before, and this is what it looks like. We have y is equal to a linear combination of regression parameters denoted by our betas and the explanatory variables denoted by x. We have also what's often referred to as a random error term at the very end of this expression. This error term has a probability distribution associated with it. It's a normal distribution with a mean of 0, meaning that on average your errors are equal to 0. And it also has a particular variance, sigma squared, which is a parameter that we would want to estimate. So the parameters here are the regression parameters, the betas, and also sigma squared. Now we could this expression is how we think about how y comes about in terms of our population itself. We could rewrite this if we wanted to focus on one particular value that maybe would occur in our sample. We could rewrite this so that we have an I subscript on the y's and the x's and even our epsilon as well. Each of these epsilons again have a normal distribution, and also writing it this way helps us also to emphasize that these epsilons need to be independent of one another, meaning what happens for, let's say, one item in your sample cannot affect another item in your sample. What we're going to be very interested in is the expected value of y with a normal linear regression model. Expected value y again represents what would you expect y to be on average for, in this case, a particular set of your explanatory variable values. And so this is what it looks like. Now you might be wondering, well, what happened to the epsilon that we saw before? Well, remember that this epsilon has an expected value of 0, so on average it's 0, and so that's why it no longer appears in there. So the expected value of y is equal to this linear combination of our regression parameters, the betas, and the explanatory variables. One can also think of now our model as basically we are assuming that y has a normal distribution with a mean of the expected value of y, this linear combination, and a variance one could show is actually equal to sigma squared. Okay, so let's put this in context of an example. Whenever I teach an introductory statistics course, I like to use this particular example where let's say that y represents college GPA, and we have one explanatory variable, x sub 1, which represents high school GPA. Now you can imagine a scenario where a college admissions office would be very interested in a model that helps you relate a student's high school GPA to how they would perform in college. The admissions office then could use this regression model to help decide who should they admit and who should they not admit to the school. And so they would be interested in this particular model. Expected value of y is equal to beta 0 plus beta 1 times x. Now, there could be other explanatory variables that would be of interest too. Maybe I have a second explanatory variable that represents ACT score. So x2 could be ACT score, and beta 2 will be the corresponding regression parameter for it. Now, a very important aspect of any kind of normal linear regression model is to understand the effect that x1 or x2 has on what you would expect y, your response, to be. And so notice what happens if, let's say, if I come all the way, I guess we can use this one here. Let me just do a little bit of erasing. Notice what would happen if beta 1 was equal to 0. Then that would say then 0 times x1 is 0, and so that x1 essentially disappears from the model. And so that x1 has no effect on what you expect y to be on average. In fact, I would expect all of you have actually done hypothesis tests concerning is beta 1 equal to 0 or not. If beta 1 was, let's say, greater than 0, then what that says is that as x1 increases, what I expect y to be on average also increases. So because of that, we often refer to this as a positive relationship. If beta 1 was less than 0, that says I have a negative relationship. As x1 increases, expected value of y goes down. And so we're very interested in interpreting the effect that x has on expected value y, and to do that we focus on the corresponding beta, the regression parameter. So this then gives it a standard interpretation that hopefully you have seen before for the effect that x has on the expected value of y. So if we just think of, let's say, one particular explanatory variable, let's call it x sub r. For every 1 unit increase in x of r, expected value of y increases by beta 1 units when holding the other explanatory variables in the model constant. Standard interpretation. Where does this come from? Well, if I were to write out my model, let's say r was equal to 1. Here's my model, and then let's say if I look at it from the perspective of a 1 unit increase in x1, look what happens. I can rewrite it like this. Notice that the expected value of y has actually increased by beta 1 when x was increased by 1. I guess maybe more simply put, this whole interpretation then comes about through interpreting what you would learn in an algebra class when you would interpret the slope of a particular line. Notice I also have that I need to put when holding the other explanatory variables constant. So if we look at a model that does have more explanatory variables, we can't have these extra parts change when we're trying to interpret the effect of one explanatory variable on the expected value of y. So these regression parameters are parameters. We need to estimate them. Typically, the way that you're taught how they're estimated is through what's called the least squares method. This method is actually equivalent to using maximum likelihood estimation in this particular case when we have this normal distribution. So that's something that's kind of interesting to know, and we'll talk about that more coming up. So once we get these estimates of these regression parameters, then we could rewrite the regression model as an estimated normal linear regression model, where I put in the numerical values for my beta into my model. Symbolically, we can denote these as beta hats. Also, my estimated value for the expected value of y becomes y hat. Then the standard interpretation for the estimated effect, that a particular explanatory variable has on the expected value of y is, well, for every 1 unit increase in x, the expected value of y is estimated to increase by the corresponding beta hat units when holding the other explanatory variables constant. Okay. A real brief introduction, or review I should say, of normal linear regression models. Now for our particular setting, y does not have a normal distribution. It's not a continuous random variable. Rather, it's a binary random variable that has that represents a success or failure. And so we're going to use y equal 1 to denote the success, y equals 0 to denote the failure, as we've kind of talked about before. And for now, just for emphasis, I'm going to add a subscript I to the y to say that this is for, let's say, the corresponding ith value, or ith item, I should say, that we're interested in. So a real brief example, suppose y sub I could be something that denotes whether the ith person graduates from college, yes or no, 1 or 0. And I could look at, let's say, maybe one explanatory variable called x of I1, which denotes the number of hours that a student studies per week. Now this y, since it is binary, has a Bernoulli distribution associated with it. The probability of success parameter for that distribution is, let's call it pi sub I. So again, we're talking about the ith item. Of course, also for Bernoulli distribution, when we first saw that, we found out that the expected value of y sub I would be then pi sub I. Now note that for a sample size n, that means I have n different pi's that I need to estimate. That's a lot. And so that's where then the beauty of using regression models comes in. Because now I could, let's say, if I have some explanatory variable that does a really, really good job of helping me understand what the probability of success is, now I could write then a relationship such as this, where the expected value of y sub I is equal to beta 0 plus beta 1 times x of I1. And so now instead of having n different pi sub i's that I need to estimate, all I need to do is estimate these regression parameters too. And then I can then use that to estimate my pi sub I. So we could rewrite then the model like this, using the equivalence between the expected value of y sub I and pi sub I for our binary response variable. Now, how do we estimate then these betas? Well, we should not do what you've learned before with a normal linear regression model, where you would use least squares estimation. Instead, why? Well, that was set up for a normal linear regression model, assuming that y had a normal distribution. Obviously, we do not have that here. Also, the variance of y sub I for a normal linear regression model is just simply sigma squared, an extra parameter corresponding to that normal distribution. Here, based upon what we've learned for a Bernoulli distribution, this variance is actually pi times 1 minus pi, with subscript I there. And so what we can see is that the variance actually changes depending upon what pi is. With a normal linear regression model, you just had one variance, sigma squared. That was it, one parameter to worry about. So what we could do then instead is use maximum likelihood estimation as what we've done before. So here's our likelihood function where we have two regression parameters. Let's say, again, we just have a simple model where we have just one explanatory variable. We have two regression parameters that we need to estimate, beta 0 and beta 1. And remember, with the likelihood function, we say that's given my observed data. And just like how we've written a likelihood function before, we write out it in terms of the product of the probability that, let's say, y sub I is equal to a particular value, 0 or 1, or let's say little y sub I. And so I can keep on writing this out, and we get exactly the same likelihood function that we did before when we let y have this Bernoulli distribution. The only difference is that I have a subscript I on the pi's. Based upon how I wrote the regression model before, well, we can just substitute then beta 0 plus beta 1 times x of I1 into there. And that's why this is a likelihood function written in terms of beta 0 and beta 1. And so what we can do is maximize that likelihood function to come up with maximum likelihood estimates for beta 0 and beta 1. Unfortunately, there's still one problem with doing this. And that is, by writing our model like this, we are not constraining it so that pi has to be between 0 and 1. Of course, pi is a probability. Probabilities are between 0 and 1. But you can imagine particular values of x, particular values of beta 1, particular values of beta 0 that lead to negative pi's, or pi's that are greater than 1. And so that is a problem. How do we solve that problem? Well, this is where then logistic regression models come into play. Logistic regression models are a type of binary regression model. They are widely used. Basically, it's the exact same model that I just showed you, but now we use a mathematical transformation with pi sub I so that it guarantees that pi will always be between 0 and 1, no matter what the betas are, no matter what the x's are. Okay? Here's what we can do. This is a logistic regression model. Pi sub I is going to be equal to the exponential function evaluated at the linear combination of the regression parameters in our explanatory variables. That's in the numerator. In the denominator, we have 1 plus the exponential function evaluated at the linear combination of the regression parameters in the explanatory variables. Well, why do we use this kind of mathematical transformation here? Well, based upon your algebra days, you found out that the exponential function, of course, is always going to be positive. Okay, so now I don't have to worry about having a negative pi value. Also, because in my numerator here, I have exactly the same thing as I have in my denominator, except for I'm adding 1 to it, then that guarantees then that this what's in the numerator and the denominator ends up making sure that pi will not be greater than 1. And so that's why we use this mathematical transformation. Now what one could do is rewrite this model using some algebra so that I only have this linear combination on the right side of the model, and on the left side of the model then I have the natural log of pi sub I over 1 minus pi sub I. Again, just through using some algebra. Make sure you can do this on your own. Here's a little bit of a hint about how to do it if you're not 100% for sure immediately. Now notice what's inside this log. Probability of success divided by the probability of failure for the ith item. This is an odds. So what this logistic regression model allows us to do is model the log odds of a success as a function of explanatory variables. Very, very interesting. we will take advantage of the fact that we're working with the log odds throughout this chapter so that we can come up with ways to then interpret the effect that X has on the probability of success. So some comments here. So this linear combination of the regression parameters with the explanatory variables is often referred to as a linear predictor. Why? Well, it's a linear combination and it helps predict the log odds of a success. This log odds that we see here, this transformation of the probability of success, has a special name in statistics. It's referred to as a logit transformation. I'll explain more towards the end of chapter 2 why it's called logit. Excuse me. But this then leads to a much more compact way to write the model, where I can actually equivalently represent the model as the logit of pi sub I is equal to this linear predictor. We can also drop the I subscript as long as there's going to be no confusion about what we're talking about here. And so we can rewrite the model one of 3 different ways without that I subscript. Note though that this leads to a little bit of, let's say, notational ambiguity with what we had earlier in my book, in my notes, where we just had pi itself. But I think in the context of what we're doing, it's always going to be clear that pi now is a function essentially of some explanatory variables. Okay, so let's take a look at graphically what this model looks like. So my corresponding code's in the program pyplot.r. And let's say that we only have one explanatory variable. So our model is going to be logit of pi is equal to 1 plus, now I have 2 plots here. The first plot is going to be 0.5 times x sub 1. Okay, that's what this is being plotted. So let's take a look at this. So we have pi on the y-axis, we have x sub 1 on the x-axis, and this is for beta 1 is equal to 0.5. Notice that that's a positive value. And so what we see here with this curve that has resulted is that the curve is always above 0. It's always below 1. It kind of has a S shape to it, which actually has a special name called sigmoidal. We see some other interesting things. So for example, if I were to draw a line here at 0.5, and if I were to take what's up here and rotate it 180 degrees and put it down below the line at 0.5, we get exactly the same thing that you see below the line of 0.5. And so because of that, we can say that this resulting model is always rotationally symmetric. Let me do a little bit of erasing here. So something else that we see here, notice that beta 1 is positive. And so we have a positive relationship between x1 and pi, meaning that as x increases, pi increases as well. Notice when beta 1 is equal to negative 0.5, now we have a negative relationship. As x1 increases, pi goes down. Let me make sure I talked about all this. Also, we can see the slope of this curve changes as a function of x. And in fact, one could do some calculus to actually show that indeed it does change as a function of x. So let's talk about how I did this plot. We're going to focus on the left plot to begin with. And actually, before I do that, let me introduce you to a function called curve. Curve allows you to simply plot curves in a graphics window of R. And let's say in a very simple case, I want to plot y is equal to x squared, or in other words, f of x is equal to x squared. How would I do that? Well, how about I first begin by looking up or opening up a plotting window with my dev.new function, and open up a plotting window in a different monitor that I'm using right now. And to plot y is equal to x squared, I use the curve function, where the first argument is expr, standing for expression. My expression, my mathematical expression, is simply x squared. Okay? I want to vary on my x-axis from -1 to +2. And so what r is going to do by default is going to evaluate x squared at 101 evenly spaced values between -1 and 2, and then plot it and connect, let's say, the points that are being plotted with a line. I'm going to make the line color equal red, put a title on my plot, put some grid lines on it. And so this is what I get. Oops, went to another window again. And so here's my plot of f of x is equal to x squared. So again, for example, what r is going to do is when x is 0, it's going to find what f of x is. When x is 0.5, it's going to find what f of x is. And if you see where my mouse is, it's going to plot those 2 points. And then it's going to keep on doing this for 99 other values that are evenly spaced between -1 and +2 for x. And then join this all with a line like this. Okay, so let's do now a plot of the regression, of the logistic regression model. Again, I'm going to open up a new graphics window, and what I'm going to do is actually divide the graphics window into 2 parts. The way that this can be done is to use a function R called par, which stands for graphics parameters. This function is used in a variety of different ways to control what things look like when they're plotted. In this particular case, what I want to do is use the argument mfrow, which stands for make frame by row, where I want 1 row, 2 columns of plots. So let me go ahead and do that. And here's my graphics window. Nothing's plotted there because we haven't actually tried to plot anything, but R recognizes that you're going to have 1 row and 2 columns of plots. So I'm going to set a value for beta 0. I'm going to set a value for beta 1. And then I use my curve function. For the expr argument, then I need to write out in the proper R syntax how to evaluate then my logistic regression model. So I use the exp function, beta 0 plus beta 1 times x, divided by 1 plus the exp function again, beta 0 plus beta 1 times x. Now, one little side note about using the curve function is that whatever you put here in terms of what is going to be varied relative to the x-axis always has to be written in terms of the letter x. It's just a rule with this function. I'm going to evaluate this from -15 to 15. We'll make it a black line. Then I do a little bit of some stuff that's kind of fancy where I get some Greek letters on my plot. You don't have to do this if you don't want to. And simply I say I want the Greek letter beta. I want a subscript, so I use a bracket 1 end bracket. I want to say that beta 1 is equal to 0.5. Well, I had to actually use a double equal there. And then I use the expression function to represent this, to tell R, hey, this is an equation that I'm working with in terms of how I want to display it in the graphics window. Do something similar for x sub 1. Do something similar for pi itself. So if I go ahead and do this, and let me get my plot, and there we go. That was the very first plot that we saw. So you can do exactly the same thing now for beta 1 equal to -0.5. Now on your own, what I would like you to do is use my program as a template to evaluate, well, what happens when, for the beta 1 equal 0.5 plot, suppose you were to increase beta 1, or suppose you were to decrease it towards 0. What's going to happen? Also, think about, well, suppose a plot of the logit of pi versus x1 was made. What would that plot look like in this situation? If you have any questions about answering these questions, please feel free to bring it up in class. So this concludes a brief little review of normal linear regression models, and then also a brief introduction to what are logistic regression model.